Take a look at all of these wind turbines. What do they have in common? 3 blades. In fact, 99% of all turbines have 3 blades. But why? Why not 2 or 4 or 10? It feels like an obvious question, but it's one worth asking. In fact, it turns out that according to the laws of physics and economics, 2 blades are actually better. And yet, 99.1% of all turbines in the world have 3 blades, with less than 0.05 having 2. But after decades of theoretical equations being brutally mugged by reality and settling for good enough, one company has finally announced that they've cracked the code, taming the very forces that turn 2-blade dreams into engineering nightmares. The question is, did they really solve it, and just how much does it matter? Let's figure this out together. I'm Ricky, and this is 2-Bit Da Vinci. This video is brought to you by Jackery. In a perfect world, on paper, 2-blade turbines are the clear winner over their 3-blade cousins. They can spin faster, generate more power, they can be more aerodynamically efficient, they're lighter, cheaper, easier to transport and install. They're even more resilient against typhoons. Looking at this amazing list of benefits, I gotta ask as an engineer, why? Why can they spin faster? Why are they more efficient? And it all starts with a turbine's tip-speed ratio, or TSR. That's the speed of the blade's tips relative to the speed of the wind coming at it. In general, a higher TSR means more power, but there's a catch. Every time a blade slices through the air, it creates a wake, a wind shadow of disturbed, turbulent air behind it. The turbulence reduces the next blade's efficiency. If the rotor spins too fast, there won't be enough time for the wind to carry that turbulence away before the next blade comes by and your efficiency plummets. So for every turbine, there's an optimal TSR where efficiency maxes out, and it's directly linked to the number of blades. Suppose you have your typical 3 blades. The first one passes and leaves a wake. The next blade will travel through that choppy, lower energy wake after 1/3 of a turn. But what if you had fewer blades? With 2 blades, the second blade passes through that same spot after a half turn. That's more time and distance, so it can get away with going faster at a higher TSR while still hitting fresh, undisturbed wind. That's interesting. The result is that each blade can extract more power from the same incoming wind. If we're asking questions, then how about this one? Why stop at 2? Why not just have 1 blade? That would be the absolute best case scenario for efficiency, since the blade travels a full turn before hitting its own wake. And while that's true, there's a trade-off. Having fewer blades means less surface area for the wind to push on. So even though a single blade is super efficient, the turbine as a whole captures less energy because most of the wind just misses it. So 1 blade, while good at one component of capturing wind, misses out on others. And 2 blades is a good compromise. But efficiency is only the beginning. Another benefit of 2 blades is that not having a 3rd blade makes the rotor almost 30% lighter, more power with less weight. So turbines get a much better power to weight ratio. Here's a comparison of the power to weight ratio of a 2-blade turbine from WindFlow. It's 20% higher than its closest competitor. A better power to weight ratio means cheaper construction, fewer materials, and easier transport and deployment for the same rated power. It's also important to note that most 2-blade turbines are often downwind turbines. We'll get to what that means in a moment, but for now, just know that it lets engineers make the blades themselves even lighter and more flexible than 3-blade designs. Another key benefit is typhoon resistance. The 2-blade design can park with its blades lined vertically, effectively shielding the rotor behind the tower and minimizing the forces from extreme wind, making it more resilient in hurricanes and typhoons. So with these benefits, why aren't there more 2-blade turbines? Why not maximize these benefits with 1 blade? The answer is that in engineering, there's always a trade-off, and in this case, several. But before we dive into that, while making this video, I had an adventure of a lifetime. I just spent a week at Burning Man with the goal of surviving some of the harshest conditions purely on solar and batteries. So how did I do? I brought this, the Jackery HomePower 3600 with 3.6 kilowatt hours of energy storage and a 500 watt Jackery solar panel. I powered a mini fridge for 8 days straight, which had all my food, a Starlink for internet, lights, and a 1200 watt induction cooktop for all my cooking. Charged all my devices and even ran a 1400 watt AC once in a while for especially hot days, all entirely from my HP 3600. The conditions were brutal, with 60-mile-an-hour winds that battered and destroyed my tent, and heavy rains that turned everything to mud. But thanks to my Jackery HP 3600, I made it all week purely on sunshine and batteries. The Jackery Solar Saga 500X solar panels help keep my batteries charged each day, even when covered in rain, sand, and mud. I laid it flat for better wind protection and saw peaks of over 400 watts. And even though my camp got more crowded and shading became an issue, these panels stood up to the extreme weather with zero problems. I even had enough energy left over to make coffee each morning for my neighbors on my induction cooktop. If it can hold up to these conditions, you know it'll make quick work of backup loads around your house if ever the power goes out. And it does all of this quietly and reliably with no smelly fumes. My Jackery HomePower 3600 was battle tested, passed with flying colors, and gets my highest recommendation. So check it out today using my links in the description and be ready for anything. Huge thanks to Jackery and you. Now back to the show. I want to introduce the company that's changing the game. Enter Envision Energy. Just last week, after over a decade of R&D, the Chinese turbine manufacturer announced a breakthrough. Their next-generation 3.6 megawatt onshore two-blade turbine prototype completed over 500 days, almost 1.5 years of continuous and stable operation. They shared some pretty impressive performance and reliability specs. The prototype is a workhorse that demonstrated high productivity, achieving the equivalent of 3,000 annual full load hours. This measures how long it would take to produce a total annual production if it operated at full power. The turbine performed on par, even better than other three-blade turbines in the same site that reached 3,000 annual full load hours. And the turbine successfully survived winds of 51 meters per second by using its self-positioning capability. Then there's the mean time between trips, which is very similar to mean time between failures, or MTBF. It's the average number of hours a turbine runs before something causes it to trip and shut down for a fix. Envision's machines ran for an average of 2,444 hours between trips. Then there's availability. What percentage of the time was the turbine ready and available to make power? Envision's prototype hit a remarkable 99.3%. For comparison, the Windflow 500, a well-known two-blade turbine, has a lifetime availability of around 95%. So we did a lot of research to figure out the historical data, all that we could find on two-blade turbine reliability metrics like MTBF, mean time between failure, and MTTR, the mean time to repair. And this is what we found. Look at how the time between failures has been steadily climbing. Back in the early 2000s, the average MTBF for a turbine was around 1,200 to 1,400 hours. Today, thanks to 2 decades of refinement, a modern, mature three-blade turbine sits at around 2,500 to 4,000 hours. Envision's 2,444 hours places this brand new, historically volatile technology right in the middle of the pack with proven industry standard machines. The time to repair has also been going down. And the reason why we're looking at this is, combined with the mean time between failures and the mean time to repair, we can figure out the availability and compare it to more traditional three-blade turbines. And this is what the numbers look like. How good is 99.3%? It's about as reliable as turbines were in the early 2000s. But to understand just how great these numbers are, we have to talk about the dark side of two-blade turbines. Besides less power generation, another issue with having fewer blades is lower torque because there's less surface area to catch the wind. This means they struggle to start turning in low wind conditions, like trying to get a heavy merry-go-round started with only one person pushing. Then there's noise. To be efficient, two-bladed turbines have to spin faster. That higher tip speed generates significantly more noise, which is a huge problem for installations near populated area. But these are minor problems. The real two-blade turbine killer are vibrations. There are 2 main sources of vibrations. The first is something called the tower shadow effect. Here's how it works. Remember how I said that these are typically downwind turbines? That comes with a major drawback. As a blade passes behind the tower, the wind is momentarily blocked or shadowed, while the top blade is getting hit with the wind's full force. This causes a sudden jolt, a massive imbalance that rocks the entire structure with every single rotation, leading to material fatigue and failure. This doesn't happen on a 3-bladed design because the rotor is in front of the tower, not behind it. Another big problem with 2-blade turbines is caused by massive vibrations when the turbine yaws or turns to align with changing wind. Now, I do understand that this is caused by the gyroscopic effect, but what I didn't fully understand is why it was so different between 2- and 3-blade turbines. The explanation I found was that the 3-blade rotors are inherently better balanced. Now, this was a little interesting, and I didn't fully understand at first, so let's figure out why. Have you ever seen the experiment where someone sits on a rotating stool and they're handed a spinning bicycle wheel? When they try to tilt the wheel axle, the stool they're sitting on starts to spin instead. That turning force they feel is the gyroscopic force. Anything that spins generates this torque when you try to change its axis of rotation. A spinning turbine is the same. It's like a giant spinning wheel on top of a tower. When the wind changes direction and the yaw system tries to turn the rotor towards it, it generates a powerful gyroscopic force that tries to twist the tower. But the thing is, both 2-blade and 3-blade rotors are symmetrical, and both are perfectly balanced. I thought they must generate the same gyroscopic force when they yaw, but apparently they don't. It turns out that as a turbine yaws, each blade generates its own twisting force on the hub, and that force depends on where the blade is in its circular path. So what's the difference then between 2-blade and 3? Well, that's where it gets a little tricky, and it's all about how these forces add up. In a 2-blade design, the blades are directly opposite each other, and it turns out this means that they always generate a torque in the same direction, which amplifies the effect. Picture it like two kids on opposite sides of a pole. One pushes while the other pulls, and they do it in perfect sync. It's easy to picture the pole swaying more and more dramatically. Since the rotor is in the same orientation twice per revolution, this creates a large pulsating vibration with two violent shoves every circle. They call this the 2P vibration, and this is what it looks like. Now, what happens with 3 blades? Well, they're 120 degrees apart, so their individual torques are also offset. So now you have 3 kids pushing, but not at the same time. Their effects overlap and smooth everything out, and the result is almost constant, gentle turning forces on the tower instead of a massive swaying motion by the 2-blade system. And that's when I realized, okay, so that's why we don't have more 2-blade turbines. This dynamic instability is the primary reason the 3-blade design dominates. The choice was never about peak efficiency. It was a complex compromise between dynamic stability, structural integrity, material fatigue, and cost. Envision Energy appears to have managed to work around these cons, though they have stood on the shoulders of all the giants that failed before them. Engineers have tried to solve these vibration problems for decades. One early solution was the teetering hub, which allowed the whole rotor to pivot slightly like a seesaw, absorbing some of the uneven wind load. Making 2-blade turbines downwind machines also helped. This means the rotor is behind the tower, so the wind hits the tower first. The benefit is that when the blade flexes under heavy wind gusts, they bend away from the tower so you don't have to worry about them striking it. This allows for much more flexible and therefore lighter and cheaper blades compared to upwind turbines whose blades must be incredibly stiff to avoid bending and hitting the tower. So have any of these designs made it to the market? In the last century, we've installed roughly 1,136 gigawatts of wind capacity, overwhelmingly with 3-blade turbines. Of that, only about 0.5 gigawatts, less than 0.05%, have been 2-blade designs. But the small fraction means a few companies have tried. And going down the rabbit hole, I found that there are actually only 8 companies currently manufacturing 2-blade turbines. You've got Envision Energy, of course, then there are pioneers like Seawind in the Netherlands and Hitachi in Japan who are still commercializing their downwind design. But the history is mostly a graveyard of failed attempts. Companies like Minyang, China's largest privately held turbine manufacturer and 4th largest overall, tried building 2-blade offshore turbines but abandoned them for massive 3-blade models, mainly because utilities simply didn't like them. NASA even tried to brute force their way out of the vibrations by making the structure massive and super sturdy, thinking that they could just withstand the vibrations. And others like Windflow in New Zealand and Nordic HomePower in the US went bankrupt trying to make it work. So what is Envision doing differently? Well, Envision's solution isn't mechanical, it's digital. Instead of just trying to withstand the wobble, their turbine fights back, using 2 key patented technologies. First is active vibration damping. While the specifics are proprietary, this involves sophisticated damping algorithms and a unique hub geometry designed to counteract the aerodynamic and structural challenges of a 2-blade system. These advanced control systems are a cornerstone of the turbine's smart technology. The system uses sensors to feel the 2P vibration starting to build up. The controller then makes instantaneous, precise adjustments to the pitch of the blades, creating an aerodynamic force that directly counteracts and cancels the vibration. It's like noise-canceling headphones for the entire turbine. Second is a rotor imbalance correction. This is a two-stage system. First, it uses the real-time pitch control to counteract any temporary aerodynamic imbalances. Then it takes further measurements to calculate if there is any underlying physical mass imbalance in the rotor. And it tells engineers exactly what balancing weight to add to the hub for a permanent fix. The turbine is built on Envision's Model X onshore platform, which features a modular design. This approach simplifies logistics, transportation, and assembly, which is a really big deal for turbines with long blades. The use of a high-speed doubly fed induction generator is another significant feature. This technology allows for variable speed operation, optimizing energy capture across a range of wind speeds and improving grid stability. I'd like to point out how impressive Envision's reliability numbers are considering the complex system and modular design. The number of potential failure modes for normal wind turbines are off the charts. I found one peer-reviewed paper that identified no less than 115 failure modes that could go wrong in a general wind turbine. The system's complexity will surely add a dozen more. And here are the failure modes for a solar PV system for comparison. The fact that the turbine has been fully operational for 99.3% of the time during the past 500 days speaks volumes to just how far they've come. So, the two-blade turbine has been reborn, vindicated by years of research and enabled by modern control theory, and it has emerged as a powerful new tool in the quest to lower the cost of wind turbines. Like many things in engineering, sometimes a technology is just too early, and it can't really take off until something else comes along. The transistor and microprocessors and computers are a good example of that. Computers completely change the game in terms of aviation, for example. You can have unstable flight patterns that you can control with computer logic that you could never have a pilot do manually. And it's kind of the same thing here. Now, with computer logic and control that can run sensors thousands of times a second and make corrections, we might just see two-blade wind turbines off in the horizon. But what do you think? How big of a deal is this breakthrough? And do you think there is a big future for a two-blade turbine? And will it start catching on in popularity? Sound off below. And until next week, check out this video next that we think you're going to like. I'm Ricky with Da Vinci. Thank you so much for watching.